Hi students, Mr. Halpern here. This is a video on redox reactions that I'm just going to lead. What you want to do is have your packet out for redox reactions, which we received yesterday in class. We're going to go through the first 2 pages on redox reactions. And as we typically do with videos, you're going to see some questions pop up that you want to answer based off of the stuff that we just talked about. So we're going to start off with a basic definition of redox reactions. Redox reactions stands for reduction oxidation reactions. And it's a combination of those two reactions. These reactions are transferring electrons from to more low energy electrons, so from high to low energy. And this is really foundational to a lot of different processes that we know. Burning gasoline, cellular respiration, if you study a little bit about the electron transport chain, photosynthesis, and all of those are redox reactions. So it's a very important process, and we're going to be applying this to art in our chemistry class. So really quick definitions of oxidation and reduction. Just as a quick review, oxidation is when a substance loses one or more high energy electrons. Right? So if you think of it kind of like this box is a molecule or an element that has extra electrons that it wants to get rid of. High energy electrons are things that electrons that would be easy to get rid of. So if you think of elements on the periodic table that have really low ionization energy, those have really high energy electrons. They have, it's really easy to get rid of those. So you would see that the oxidized substance is the thing that gets rid of or loses electrons. And it gives the electrons away to the reduced substance. So reduction is when a substance gains one or more electrons. And so when we give these electrons over, this oxidized substance changes electrically. Same thing with the reduced substance. And we have a nice, easy to remember acronym for this, oil rig. Oxidation is losing and reduction is gaining. What are we losing and gaining? Electrons. So examples of questions I might ask, if you see that a formula is showing zinc metal, for example, and you see that it's suddenly becoming more positive. Well, how do things become more positive? Well, the electrons are the only thing that can move, and if you're becoming more positive, most likely you have lost or given away your electrons to become more positive. So if you're giving away electrons, you are being oxidized. So that's just an example of a type of question that you could see. And as an example here, I have another one, copper and silver. So silver is positive when it makes an ion. It often becomes +1 because it has given away its electron, and because of that, it often attaches to an anion like nitrate or phosphate or sulfate or chlorine or beryllium. And so when we put it in solution and we add copper like this, copper wants to get rid of electrons. And in fact, it wants to get rid of electrons more so than silver wants to stay as a cation. So what it's going to do is it's going to get rid of an electron, and actually copper becomes a +2 ion. So in fact, it's going to get rid of 2 electrons. And what we see here on the bottom is exactly what we're talking about. So what you see here is you see copper, which was neutral, has become positive because it gave away 2 electrons. And where did those electrons go? Well, silver got those electrons and became neutral. And there were two silver atoms. Therefore, each one got one electron, right, making it possible. We have to have two silvers here because, again, copper's oxidation state is +2. And so in order to get rid of both of those electrons to make it +2, you would have to have two silvers. Each silver always makes a +1 ion, so you have to have two. So as we said, copper, because it lost electrons, is being oxidized, and silver is becoming reduced because it is gaining electrons. And this reaction actually occurs because when we think of things that are really reactive, particularly metals, as you see on this list here, this is something called the metal activity series. There's a list of metals that are more reactive than others, and copper is slightly higher on this list than silver. And because copper is slightly higher on this list, copper is going to want to give away its electrons more so than silver, and so it forces the reaction to the right. So we can write these reactions as separate reactions of just oxidation or just reduction. They're called half reactions, okay? And half reactions for this particular example would be the copper becoming an aqueous solution, meaning that it would be binding with another molecule or atom and dissolving in water. And we would show that it going from solid to aqueous, and we'd have two electrons separating from this copper. So we have it as a plus and then another product. Rather than it being, as it's shown here, copper solid with the two electrons making it neutral, it's now a cation, and that cation has lost those two electrons. So that's why it's +2e. So copper has become, if we wrote this as a name, it'd be copper 2, copper Roman numeral 2. And on the other side, we had silver gaining those electrons. So copper had to lose them, and then silver, each one took one electron each, and that became a solid silver. And in fact, this is actually how we purify a mixture of substances that has something we want, like a mineral like silver. When we go to find gold or silver as like a nugget, when we're panning for gold per se, what we do is we often put it in with a more reactive metal. And when it's in solution, what will happen is the more reactive metal will add electrons to the less reactive metal, in this case silver, and then silver will be coming out as a solid. And you'll see, in this case, silver is a very lustrous gray color, and so the solid material would go from being a copper color, which is like a pink or an orange, to a gray lustrous metal being silver. And that's how we would get silver out of solution, which is cool. So redox reactions are just a combination, therefore, of an oxidizing half reaction and a reducing half reaction. So basically, again, what I just did was I was showing you the full reaction, breaking it into half reactions, as you see there, and then you see the full reaction again. All right, so you can see how we looked at it, pulled it apart, and then put it back together. Okay. Sometimes I might ask, if I give you the full reaction, can you tell me what the half reaction is for oxidation? In which case you'd have to know how to write an oxidation half reaction and which one is actually the substance being oxidized. So if you again look at copper, copper went from being a neutral solid substance to an aqueous cation. And that implies that it lost electrons. So if we remember oil rig, oxidation is losing, therefore copper, because it lost electrons, is being oxidized. So we'd write out CuS and then yields, which is the arrow, and then Cu plus 2 aqueous, and then add the 2 electrons at the end, showing that it lost those. Okay, so moving on to the next page. On the next page, we are going into Lewis dot structures. So we know what Lewis dot structures are. These are representations of atoms and compounds that have dots representing the valence electrons. And what it does, it helps us to know how many bonds something can make and also how many electrons it would want to give away as an ion. So again, for the example of what we just did, copper and silver, again, the half reactions are there. And what I showed you here is the non-Lewis dot structure versus the Lewis dot structure, what you would show. And again, what you see here is really the movement of electrons. You see that the electrons were originally in the copper, and over the course of the whole reaction, you see that the copper gave the electrons over to the silver, right? We start with copper as a solid, and on the right-hand side, we now have silver with these 2 electrons, and it's now solid. That's a picture of Lewis. So this is another example here, and we'll pause this for a second. Maybe you can figure out what is being oxidized and what's being reduced. So if you looked at this, you saw that the manganese, the Mn3 plus, was going from a cation to becoming a solid neutral atom. And so because of that, it had to gain electrons to become neutral. And so therefore, because it gained electrons, it's being reduced. Remember oil rig, R-I-G is reduction is gaining electrons. So manganese is now a neutral atom because it's being reduced. And then conversely, therefore, sodium, the solid, was being oxidized. So NaS is being oxidized because it became a cation, which means that it lost electrons. So because manganese is being reduced by sodium, because sodium gave up its electrons, sodium is the reducing agent. So this is a little bit confusing, but it's something that you should make intuitive sense. If manganese is the one being reduced, then the thing that helps it be reduced is the reducing agent. And how did sodium help it? Sodium gave electrons to manganese. And so we call that sodium the reducing agent, right? Or the reducing helper, if you want to call it. But it's technically called the reducing agent. Conversely, sodium, Na, is being oxidized by manganese. Why? Well, manganese is accepting the electrons. So it's helping sodium become oxidized. And so as a result, we call the manganese 3 plus the oxidizing agent. Oxidizing agent. And so we have a couple of examples here you should try.